So we'll continue talking about the second law, thermo. We've just derived this expression here. This is the second law of thermodynamics as it gets applied to a process from state one to state two. And then we talked about that same expression then per unit mass and per unit time. Now, from there, we've introduced this idea of the entropy generated, right? That last term in the second law. That basically what this does is this satisfies this entropy generated satisfies the inequality. We're converting an inequality to an equation to get this. But in order to preserve the inequality, the rules of the inequality, we have to talk about this entropy generated term, the S-gen term. Now, we've talked quite a bit about a reversible process, and that for a process to be reversible, that means you have to be able to get both the system itself and the surroundings back to their initial state. But we're not going to be able to do that. We talked about different situations where that's really not possible. Either the system or the surroundings is going to be changed long term. And you're not going to be able to get both back to their initial state. So that the difference of how far can you get the system and or the surroundings back to their initial state, that difference basically, or the sum thereof, represents the entropy generated and is now out somewhere in the universe. And to the best of our knowledge, we cannot destroy it. So the entropy generated, and I always come back to my bottle of water here and say, well, if we talked about if I put this in the freezer and I remove a whole bunch of entropy from it, basically if the water is the system and I decrease the entropy of the water, well, how do I do that? Well, I have to put it in a refrigerator, and that refrigerator is going to kick out a bunch of heat, all the heat out of the water and the additional electricity needed to run the process. And all that's going to go out as heat out into the surroundings. So I can decrease the entropy of my system, but to do so, I end up increasing the entropy of the surroundings. And vice versa. Basically, a heat pump is a device that decreases the entropy of the surroundings, but it increases the entropy of the system, right, by doing so. And what we find, again, for this inequality to be preserved, we basically have said, well, this entropy generated basically accounts for how much that this is bigger than that. And so there's basically rules associated with S-gen, the entropy generated. And the rules are essentially that the entropy generated is going to be greater than or equal to 0. S-gen. Pen just decided I didn't want to write. That entropy generated is always going to be greater than or equal to 0. That's the rule. Basically, if you have a positive, if you use your second law equation here and you compute the entropy generated and you get a positive quantity, that just simply tells you the process is perfectly normal. It's an irreversible process. If you calculate the entropy generated is 0, then that just tells you have the absolute best case scenario. It's reversible. Or if the problem statement maybe tells you that the process is reversible, that means you can set S-gen equal to 0. If you find a situation where you have negative entropy generated, the opposite of entropy generation, that is the destruction of entropy. If you determine that you have destroyed entropy, and this goes for my students, this goes for anybody out there on the internet, I want you to do two things. First thing I want you to do is I want you to double check everything. I want you to check all your units. I want to check whatever devices you're using to take measurements, make sure they're working correctly, make sure you have the right units, make sure all your measurements are good and your algebra is good. And if you think you've figured out how to destroy entropy, and again, this goes for my students and anybody on the internet joining us, don't tell anybody. Call me. Find a way to get to me. If you figure out how to destroy entropy, come talk to me. we're gonna be rich, like absolutely rich. We're gonna save the world. We're gonna solve all of humanity's problems. Amazing things are gonna happen, but we are gonna get really, really rich very quickly. So don't. And that I've been telling students that for as long as I've been teaching thermodynamics, which is going on 20 years at this point. And I've got students that have finished PhDs at this point. And I have yet to have anybody come back and say, "Hey, Steve, I figured out how to destroy entropy." I did have a company one time. I tell this, a story about a company one time that wanted to show me their device that was they needed to know how big of a motor to hook up to a device. They didn't give me a lot of specifics, and I looked at it. I'm like, so you're taking a motor to turn a generator to generate electricity. You're using electricity to turn a generator to generate electricity. Is that what you're doing? Oh, well, we didn't say that's what we're doing. No, you didn't say that's what you're doing, but anybody can see that's what you're doing. Well, yeah, that's kind of what we're doing. We think we've got this amazing device that can generate more electricity. No, you don't. You're destroying entropy when you do that. And of course, that doesn't mean anything to anybody that has never gone through this derivation. I digress. So you just understand, I'm going to be very skeptic when you tell me you think you figured out how to destroy entropy, but I will definitely listen. All right. Okay. So to the best of our knowledge, we do not believe that we can we can have negative entropy generation. We believe that either in the system or the surroundings, there's now more entropy somewhere. And even if I decrease entropy in one of those, I increase the entropy of the other one by a larger amount. Okay? So, with that in mind, here's a nice simple example. How am I on time? Yeah, we could probably work through this. This video might get a little long. That's okay. Nice simple example, and I can pause it in a few places to kind of keep this video short. So we have a rigid, well-insulated vessel. Some of you guys, I'm hoping many of you have seen me do this already at this point. I'm going to write out my givens. There's kind of a problem statement we might see in a textbook. And I'm going to write out my givens, and then I'll stop sharing screen so we can see this bigger. But for the moment, I'm just going to write these down. 2 kilograms of a saturated, so I've got water. It's a saturated mixture. They've given me the quality is 0.25, 25% in the vapor phase. And they've given me a pressure. P is equal to 100 kilopascals. Now we're going to add electricity. We're going to add or some sort of an electronic device, some kind of a heater in this case. It's going to be turned on until all of the water vaporizes. So I've got 2 states here. So this is my initial state. My final state, we're going to go right to saturated vapor until all the water vaporizes. They didn't say anything about going beyond that. They've not given me a final pressure or temperature. So all I know is I'm just going to assume that we're going to go right up to x2 is equal to 1. And we want to know, so we want to know how much energy is this electrical device put into the tank, and what is the amount of entropy that has been generated as a result of this process. Now, there's one more given, actually, there's 2 more given things here that I've not included in what I've written down yet. Pause it and see if you can figure out what those are. Okay, did you pause? Did you get it? You know what those are? What are the 2 things that are given that I've not written down here? Remember early on, I talked about multiple times, I think I've talked about what do the adjectives mean? Rigid means constant volume. This tank, this vessel, is the boundary is rigid. It's not changing shape. Rigid in an engineering sense often just means that it's not changing shape. In this course, what that means is the volume is staying constant. And it's well insulated. So there's no external heat crossing the boundary. The only energy crossing the boundary is going to be work, and we're going to assume that it's a closed system. They've not talked anything about mass crossing the boundaries. Often just with a rigid vessel, that's what we're looking at. Okay, so if we set this up, right, what are we looking for? We're looking for the electrical work coming into this device. And here's where I say, all right, well, where should we start? What's a good tool for trying to find an unknown energy? And the hope is at this point it's a gag reflex. And you say, first law. All right, good. How do we write a first law equation? Well, you draw your system. You draw any energies crossing the boundary. It's going to be electrical work. It's insulated, so you can draw a little shading around the border if you like. There's no heat transfer, and we're assuming that it's a closed system, so there's no mass. So that means the entire first law, the entire left-hand side of the first law equation is the electrical work. And that's equal to the change in the energy of the system. The energy of the system could be internal kinetic or potential energy could be changing for the system itself. It's probably a stationary system, so I think it's safe to assume the internal energy is the only thing changing. Okay. I'm trying to find this electrical work. Um, I do know the mass. The internal energy are property values. How do we find properties? Well, there's a set of rules and it's different for every substance. What is your substance? I have water. Okay, since I have water, that means I need to use properties to find other properties. I need at least two. I know the initial state and the initial pressure. That will be enough to get me, right? So given P1 and X1 will be enough to give me U1. And what do I know about state two? And so here's where I'd say, all right, well, what do I know about state two? And this is how you should approach your homework problems and the test problem. Be all right, well, I need to figure out U2 now. How am I going to find U2? I need two properties to find U2. What do I know about state two? Well, I know state two is saturated vapor. At least that's what I'm assuming. What else do I know? And somebody said, well, is the pressure the same? No, pressure is not the same. We don't know anything about the pressure at state two. That's not given to us. So what do we know about state two? And often kind of a giveaway is might be, well, is there anything that's constant between these two states? That's often helpful. Yeah, the volumes are constant. Since the volumes are constant and the mass is constant, their ratios, the specific volume, because specific volume is the ratio of volume to mass, both volume and mass are constant, so their ratios, the specific volumes are constant, meaning I also need to get the specific volume from state. Okay. This shows me you know how to get to the electrical work. You've identified everything else this is given. You've identified what you're going to use correctly to get these other properties that you need. So that's a good start. Okay. Are we done? Well, no, remember the problem asked for two things. Okay, so we've used the first law to find this unknown energy. The problem's also asked about the entropy generated. How do we find the entropy generated? And I'll say, okay, what tools, laws, or relationships do we maybe have that would allow us to quantify something about entropy? And often, if we're standing in the classroom, I probably have some version of the second law at the board behind me, and I wait until somebody says either the second law or maybe somebody points to the board and says, "What about the second law?" Yeah, I think the second law works just fine. We've got a process from state one to two, so we can use the version of the second law for process from state one to two that says the change in entropy is equal to the total amount of heat transfer divided by temperature that occurs from state one to two, plus the entropy generated, what we're looking for. Entropy generated, this is the guy we're looking for. So how do we find this guy? Well, these are total amounts, meaning I need to find I'm not going to find big S in the property tables. What I will find is little s in the property tables. Now, what do we know about the heat transfer? All right, here's where I'll ask the class. What do we know about heat transfer? And I'll wait until I get an appropriate answer. And hopefully somebody will say, well, it's well insulated. That means there's no heat transfer. That's right. So, and I always like to ask this question. What happens? Remember, an integral is just what happens when we add up a whole bunch of little tiny things. And so I'll ask the class, what happens if I add up a whole bunch of little tiny zeros? What do I get if I add up a bunch of little tiny zeros? And hopefully somebody says, well, you get zero. Yeah, because there's no heat transfer. If I add up all the zeros that are the heat transfer, that's what I do with an integral. I get zero. That's a common thing we can do with this crazy partial integral. If it's adiabatic, well insulated, negligible heat transfer, that all those tell us you're adding up a bunch of little tiny zeros. Just set that equal to zero. Good to go. Add to that the amount of entropy generated. Again, we know the mass. Now we go through, okay, what do we know? What do we not know? Can I solve? All right, well, I know the mass, that's known, right? That's up above. These are properties. Same rules apply. I need to know my substance. It's water. Okay, well, I can use property tables. Oh, look here. I've already found a path to get properties at these states. So I can also, when I'm getting these other properties, I can also go ahead and get the entropy values. So once I get the entropy values, notice now SGen and the electrical work, these are the only two unknowns that I've got. I just need to go get properties. If this were a test problem for me out of 25 points, I'm probably going to give you like 8 points for the second law being correct and correctly simplified, 7 points for the first law being correctly simplified. Those are the two fundamental equations needed to solve this problem. I try to throw 15 points at those. 5 points of getting all the properties. I would probably do 3 points on these properties because you got to use equality here. These properties you're just looking up. So I might do 4 points for these and 1 point for these because these are just going to look up. Well, no, you probably have to interpolate between volumes. So you probably have to interpolate these. So 5 points for your properties, a little bit of math to get there. That happens. And then the remaining 5 points would just be getting to final answers. So I might even do like 6 points on properties since you got to do a lot of math on both, and then 4 points, 2 points for each answer there. Okay. Let's go look at answers, right? I've got answers here, so we can go look at those. And that'll make a nice stopping place for this. I think I've got answers in here. Let's see. Yeah, so there's properties. For state one, these are using sixth edition values out of the Changle and Bowles text. It's my guess is those are sixth edition, but for water, that those properties probably haven't changed much. Go ahead and do those, right? Do these, check these values, make sure they're okay. And then before I reveal these next ones, I would say pause. And before I reveal these next ones, see if you can figure out these. You're probably going to have to interpolate because your volume is probably not going to line up perfectly, but you're looking for a saturated vapor that has the same volume that you see here at state one. So we're looking for saturated vapor at this volume. So go ahead and pause and work that out. You're probably going to interpolate these two, see if you can get answers there, or at least see what they should be between. Okay, do you have an answer? All right, I'm going to go ahead and reveal. So again, you would have to interpolate these two values. I'm almost certain this specific volume, you're probably not going to find saturated vapor with this exact specific volume. You're going to have to interpolate probably these values. But once you've got all these again, now it's just plugging in numbers, getting to an unknown. And that's the reason I don't really put near as much points on getting the right answer so much as showing me you know how to, given an infinite amount of time, I know you can get to a solution if you'll show me this. So I'm going to get you to a passing grade if you'll show me this. Okay. That's my philosophy. I know not all engineering faculty have the same goals I do, so sometimes they have to have a different philosophy in their grading, and that's okay. It's not their fault. All right, that's a nice enough place to stop this video and move on to, I think that might take us to, yeah, that takes us at least to the last part of this lecture.